About a year ago, I made a video about a homemade grid-tied inverter. And in that video, I connected my contraption to a power outlet, and right before I turned on my device, we were able to observe the voltage on the power grid, which of course looked like a sine wave. But in that video, we noticed how the sine wave didn't look perfectly clean, but instead the tops of that wave were sort of flattened, chopped off. I don't know what the right way to say it is. Now, as I also explained briefly in that video, this is because of how a lot of modern day power supplies work. And in this video, we're going to talk about this in a little bit more detail. So a lot of modern day equipment runs on low DC voltages. Think of things like phones, laptops, computers, TVs, but also things like LED lighting. A lot of old school lighting would run directly on mains power, not so much for a lot of LEDs. And so to create this low voltage DC for all these things, they need a power supply, right? A device that converts mains voltage AC into the DC voltage that they need. And if those power supplies are not designed properly, they can cause the problem that we just talked about. And that goes further than just being, not visually appealing on an oscilloscope. It also means that these things can have a really bad power factor, which can have large consequences for the power grid. So why don't we start by taking a look at how one of these power supplies typically works. So I have a whiteboard here with some drawings on it, very exciting. Let's take a look. So a lot of power supplies these days have an input stage that looks like this. And it's a picture that you might actually recognize. This is what's called a full bridge rectifier, which for some reason is quite a popular circuit on the internet nowadays. I think it's got to do with some YouTuber. So the way this works, just in case that you don't know yet, a full bridge rectifier essentially turns AC into DC in a very elegant way. And it does that by making use of the fact that those diodes are essentially like check valves for electric current. So the electric current can go through them in one direction, but not in the other. And so the way that that applies here is, let's say that you have your AC voltage coming in, right? It's a sine wave, and it goes positive first. So if it goes positive, this side becomes positive, so plus sign, the current goes that way. The current can then be pushed through this diode, and it comes out right there. So this is your positive side. This diode here will be blocking, because the current can only go through the diode in this direction. The other side will be negative, so current will be going that way, and so that current comes through this diode here, so the current can return into here, so that it runs through this diode, and then that way. So this is your negative side. So now what happens when the grid voltage goes negative? Well, when the voltage goes negative, so this side becomes positive, and this side becomes negative, your current on this side will be going that way. So it'll be going here, and this time this diode will actually be blocking it, so the current can push through this diode, and it still comes out here on this positive side. So this doesn't change. Same if you look from this side, your current here will be going that way now. So the current can go from here, in here, push through this diode, and then return that way. So if you flip the polarity on this side, it still remains the same on the other side. So this is how you can rectify an AC input into a DC output. But the problem is it will not be a perfectly flat, smooth DC output. It'll be a very bumpy DC, because essentially all this does is it takes the negative half of that cycle and just flips it up. So what comes out of this looks kind of like this. So now you still need something to turn that into a nice smooth flat DC voltage, and for that you use a capacitor. So basically what they do, I'm just going to remove these marks because they're no longer relevant. Basically what they do is just they put a big capacitor right here, just like that. And what that will do is it'll charge up, and then you'll sort of smooth out this voltage. Charges again, and then it'll look kind of like this. And there will still be a little bit of ripple depending on how much load is on this, so how much current is being drawn and how big that capacitor is. The bigger you make that capacitor, the smoother and the flatter you can make that voltage. So now you're stuck with a high DC voltage, and actually that is a pretty high voltage because the RMS voltage on the power grid here in Europe is 230 volts AC, which means the peak voltage of that sine wave is actually around 325-ish volts, I believe. So the voltage on this capacitor, that DC voltage, is going to be very close to the peak of that sine wave. So it's going to be around 300 to 325 volts DC. So this is a pretty high DC voltage right here. And so then the next step that you're going to do is you're going to take that and you're going to feed it into, it's going to be a really pretty drawing, a DC converter. There we go. Just going to draw the simple symbol for a DC converter. There it is, a switching DC converter. That's why it's called a switched mode power supply. And there's a whole variety of different style DC converters that could be used. We're not going to go into those in this video. But basically what that does is it takes that high voltage DC and converts it into some lower voltage that could be used to power your laptop or whatever this is. And that's basically well, at a super basic level, the layout of a modern day power supply. So now let's talk about the big problem with this. The big problem is the current that it draws on the input. So to understand that a bit better, I've drawn this picture over here, which is essentially a zoomed in version of our AC voltage. So this is the voltage on the input of our power supply, a nice sine wave of the power grid. So what happens is, let's say that we are at this point in time, right there. And we're going to assume that this power supply has already been turned on a while ago. So this capacitor is already charged. So it's already sitting at, 300-ish volts or whatever it may be. So this thing is already fully charged. The DC converter is already running. And we happen to be at this point in time. So at this point in time, the voltage on the grid is 0 and there is no electric current. Basically nothing is happening here. So what's going to happen now is the voltage on the grid starts to rise. So it goes up, up, up. And while this happens, there's still nothing going on because the voltage of that capacitor is like above 300 volts. And so, we're at 10 volts here, nothing happens. We're at 20 volts here, nothing happens. We're at 30 volts, 50 volts, 100 volts, nothing happens. Because as long as the voltage here is lower than the voltage here, no current's going to be pushed that way, right? Only when this voltage exceeds the voltage on the capacitor, only then will we get current this way, and will that capacitor be charged. So for a very long time, nothing happens, nothing at all, and then, when that grid voltage exceeds the voltage of that capacitor, then we'll get a sudden spike of electric current charging that capacitor, which will last pretty shortly, because a few moments later the grid voltage will dip below that threshold again, and the current will stop. Actually, I'm just going to draw the current a little bit smaller. So right away, whoop, the current goes right back down. That's pretty ugly. Let's try that again. Just like this. So that is our sort of charging pulse of that capacitor. And the same thing is going to happen on our negative cycle, like this. And so that is what the current waveform looks like on a power supply like this. These very narrow pulses that happen right near the peak of your sine wave. And it is only during that time that the capacitor is being charged. And so that can be, if this is a high power device, like if this is a high power power supply, you know, someone's gaming computer is connected to this, who knows? Maybe they have an NVIDIA graphics card, you know, it uses 900 watts. You know, you can imagine that those pulses can get really, really big because they're very short in time. So if you have a powerful thing that needs a lot of energy, it means you need to get a lot of energy in a super short pulse, so it's going to be very large in amplitude. And you can already kind of see how that might not be very good. You can also see how this sort of flattens the sine wave a bit on the power grid, because if you have millions of devices doing this, all drawing a sharp pulse of current at exactly the same moment, you can kind of see how that sort of starts to flatten that sine wave at that moment. Right, so what about power factor? Well, let's think about the RMS current, the root mean square, or the effective current that this is drawing. So let's take one of these half waves and zoom in on it a little bit more. So I have this other chart here as well. So we have time on this axis, we have current on this axis, and here is our pulse of electric current charging that capacitor. So this is one of these pulses. So in this case, we're going to assume that it has a peak value of 6 amps. And to simplify things a little bit, I'm also going to assume that it is a perfectly square pulse. Of course, in reality, it will not be like that, but it's good enough for this approximation. So what is the RMS current in this situation? Well, what we can do is we can divide this period into 5 chunks. So here, 1, 2, 3, 4, 5. And first of all, root mean square. Let's just do the operation, right? So root mean square is the root of the mean of the squared values. So the first thing we need is the squared values. So this value is 0. If we square that, boom, it's still 0, nothing. This value is 0, square it, still 0, 0. This value is 6, square that, get 36. Okay, so 36, there we go. And then again, here we have 0, there we have 0. Okay, so we have the squares. Now we need the mean of those. So basically, we add them all up and we divide by 5. In this case, that's just going to be 36 plus a load of zeros divided by 5, which would give, let's just write it down, 36 divided by 5 is 7.2, right? That is our mean, the mean of the squares. And then we take the square root of that, so square root of 7.2 is, according to my previous calculations, around 2.7 amps. So 2.7 amps is our RMS current. So that is the effective electric current that, let's say, a wire experiences if you hook up this power supply. So basically what this means, if in case you're not familiar with the RMS value, is if you have a wire and you have these 6 amp pulses going through that wire, to the wire that feels the same as if it's 2.7 amps continuous, 2.7 amps DC. So what about power? Well, power you can calculate in a few different ways. First of all, you could calculate the apparent power. So the apparent power is just the RMS current multiplied by the RMS voltage. In this case, that would be 2.7 multiplied by 230 volts, which is around 617 watts. No, not watts, right? Because apparent power is measured in volt amps. Okay, so volt amps. This is not real power because it doesn't take into account things like phase shift and distortion, and you're about to see why that matters. So During this time, during that pulse, we are drawing 6 amps of electric current, and it is right near the peak of that sine wave. So I'm going to say the voltage is, say, around 300 volts. So the power during this pulse is approximately 6 amps times 300 volts, which would be roughly 1800 watts, right? A pretty large amount of power, but of course that is only during this very short pulse. The majority of time there is no power, it's zero. So what we have to do to get the average power consumption, which is the actual power consumption of our system, is we simply take the average, so we divide that number by 5, because we have 5 chunks here. So 1800 divided by 5, and that would give us 360 watts. That is the actual real power consumption of our thing, whatever this is, which is quite a bit less than 617 watts or 617 volt amps. So if you purely look at the electric current, you would expect this to use 617 watts, but actually it's only using 360 watts, which means its power factor is 360 divided by 617, which is like 0.6 or something like that, 0.5, 0.6, some stupid low number, really bad. Another way to look at this is that we are using way more current than necessary to get this amount of power, because some quick maths reveals that at 230 volts, about 1.7 amps should be enough to get 360 watts, and we're using 2.7, so that's not very good. Now, on a personal level, if I were using this power supply, it wouldn't matter at all, because the wires that I would use to connect this to my power outlet, they can handle 2.7 amps. Why would I care if it's 1.7 or 2.7? The wires in my house will be fine with that. Yeah, it's not a big deal. Also, my energy, my power meter is not going to count this, it's going to count this. So the electricity meter in your house that actually determines your power bill uses the actual power consumption, right? The energy that I'm using, that's this. So it's not like I'm paying extra money for this. It's not like it's less efficient. This is not the same thing as efficiency. So on a personal level, on a user level, in a lot of cases, this is not relevant, right? You wouldn't really care about this. But on a bigger scale, like in the bigger picture, this is a big problem, because if you have millions of power supplies like this on the grid, all doing this, you can imagine you can have insane amounts of extra electric current that you have to transport through all of those high voltage transmission lines, only because power supplies are doing this. And that's not very good, because grid capacity isn't free. Luckily, there is a few options that you can use to counter this, to sort of solve or mitigate this problem. The first thing you can do, and that's actually the simplest solution, is called passive power factor correction. And what this means is that you insert passive components to correct the issue. So the easiest way to do it would be to insert a coil or an inductor before your bridge rectifier. So what this means is, because of the inductance of the coil, the current that charges the capacitors will take a little bit longer to ramp up. And at the same time, when the voltage goes down again on the grid, the current will take a little while to sort of decay because of that inductance again. So the inductor will sort of spread out the current a bit more, make those spikes less sharp, and improve the power factor of the system. The disadvantage is that this inductor needs to scale up with power. So the more power your power supply has, the bigger you need to make this inductor, and at some point it sort of starts to get impractically bulky and heavy. So this is not really a good option for really powerful things, and also it's difficult to get the power factor really good with this method. It'll still be quite distorted. The second option, which is actually super popular in things like computer power supplies, is active power factor correction. So in this case, what you do is, instead of connecting that bulk capacitor directly to your rectifier, you take those apart and you shove another DC converter right in between them. And this DC converter is usually a boost converter, so it's one that can take a lower voltage and convert it to a higher voltage. And so the trick here is that even if the voltage on the grid side or the rectifier side is low, let's say 20 volts, this DC converter can still draw some current from that side, boost it to a higher voltage, and dump the charge into the bulk capacitor on the other side. And so basically, with a bit of control magic, you can make it such that this DC converter draws an electric current that follows that same bumpy shape on its input. And so the input current before the rectifier will look like a clean sine wave, which is perfectly in phase with the voltage. And so with this technique, you can achieve power factors that are very good. So typically more than 0.9, but easily as high as like 0.99, crazy stuff like that. So anyway, there you go. That is a bit about modern day power supplies and why their power factor can be so bad. That is, if they don't use some kind of power factor correction. If you enjoyed this video, maybe consider clicking the like button or even subscribing to this channel. And all that's left for me is, of course, to say thank you very much for watching.